Okay, so in this video, we're going to introduce PixelCNN and PixelRNN. These are also auto-regressive models, but they are dealing with the generation of image data. So the major reference is the original paper, that is the 2016 paper, and the 2016 another 2016 paper, and also there's a reference implementation in TensorFlow probability distributions. So basically, when we're applying autoregressive model to the image, one straightforward way is to do some order. We order the pixel one by one. Although the layout of pixel is in two-dimensional, we can still do can still have some reasonable ordering of these pixels into a linear ordering one by one. So maybe the start from the top left and go down to the bottom right. And after we give ordering of the pixels, then we can do the same things because we have we usually consider it as a square image. So there's n square pixels. So for each I minus 1 pixels, so for each previous pixels, we use this information to predict the probability of what next pixel would be. So these are some examples. We give some few given pixels and using this pixel to complete the rest of the images one by one. So this one is the results. Okay. So basically, in the terms of this paper, this is called the context. So given context, we are going to. So if we are considering pixels, then we are the previous the order. If we are already given an order, the previous pixels are the context. So by given context, then we can predict the next one. So because this is an image, one thing need to consider about it is that the image is usually very, very big, and usually there are some sort of very long distance connection between the pixels. So although in principles this one is conditioned by every single point before it, however, it is usually very it is usually very not for a lot of sequence, the newer the element is, then the more important it is, but this is not the case for the image. Sometimes the further away pixels are as important as the near pixels, because there has some continuous probability between them. So if we know what this pixel is, maybe these two pixels are not that important, but maybe this one, because it is far away from here, so this one might be more important than say this one. Suppose we already have these two pixels, then this one might not be that important, but this one is more important than this one. So in this case, we have a multi-scale context, so that we can easily to get information from far away pixels. Another thing need to be considered is we are not usually always dealing with image with single color. We are usually dealing with image with like RGB, so as 3 channels, like RGB channels. So instead of considering each pixel as an element as an item, we consider the channel of a pixel as an item. So although these 3 channels are in the same pixels, we can still need to give them an order. So you have to be very careful that you don't have information of any items, even if you are in the same pixels, because B is after G, so you cannot have the information of B to do the prediction of G. This is like if you already know the future. If you want to predict the future, you should not have the information come from future. Then that is not a prediction, a proper prediction. So of course, what if we consider this as a factor? Because I mean, this seems to be a little bit complicated, right? So why not just consider these three guys, I mean, to be a factor? So if we have RGB, then we just simply have a size of 3, a factor of size of 3. Then we consider this one as one element. Because I mean, the autoregressive can apply to a sequence of vectors. For sure, that's no problem. However, in this paper, one significant contribution or the spatial feature is it cannot do so. The reason is, although if we wish to do consider this RGB as one single factor of size 3, we need to consider the value of any intensity of color to be in a continuous space. So previously, a lot of people has already considered autoregressive model to do the image generation, but mostly because this is the most straightforward. So this is, you can imagine that, and it might just be the truth that most of the previous approach are using continuous distribution to do so. Just like as we said that because the color, the intensity has order. If the color is like the value of this red color channel is like 127, and our prediction is like 126, it is better than the other prediction. Like if we just simply predict it as like 3 or 5, 126 is more close to 127 than like 2, 3, or maybe 225 or something like that. So it has an order. So it the most straightforward or the default space for this one is the continuous space for doing the regression. However, in this paper, it says that it discovered that using a discrete distribution is better and easy to learn. So it actually doesn't so for the it actually treats the 256 distinct intensity of a channel like 256 discrete tokens, discrete values. So for each prediction, it predicts kind of like a classification to choose one thing out of 256. So for each, let's just say for each channel of this pixel, the prediction is done discretely. That is, we are treating this as a classification problem. So we give the probability of each possible values out of 256, and does not consider. So if the ground truth is 127 and our prediction is 126, it is a miss, totally miss. It is as bad as if you predict it as 0 or 255. It is a total miss. They are equally bad. So this is the setting of this paper. So why? So because of this, you cannot treat these three guys as one element, because this one will have a lot of different disadvantage. The most straightforward, if we already make it as a discrete values, then it probably you just simply do what they did right here. Treat the RGB channel of each pixel as different element. So why is this one get better than the previous approach, not using continuous distributions? The reason is that it's probably this one is a very complicated job. So although it might be more correct to use continuous values because it as both the input and the output. The thing because it provides more meaningful loss function and the meaningful informations. However, continuous distribution is very difficult to handle. Much difficult than discrete discrete distribution like the standard one, like the multi-monomial. So because this one is a difficult problem, so although the discrete setting is not optimal, but it is easier to track. So that may be why PixelCNN are more successful than the previous approaches. And even with this intuitive, more easier setting for training, the architecture of PixelCNN is very it's kind of decent and advanced, very advanced. So that might be another hint that this one is a difficult problem. So you have to put all your effort to solve it. So one of the one is using a discrete distribution to do so. Okay, so there are many different ways to do that. One where in the paper proposed a lot of different ways to treat image generation as a sequence, autoregressive sequence generation things. So another way to do that is to they call the raw LSTM. That is, it treat it unlike the previous one that treat each one as each channel as a element. It treat a whole row as element. So it kind of solve one problem, that is the ordering, because there's no totally satisfying ordering of the pixels because they are on a 2D layout. You can do some, but nothing feels really totally satisfying. However, if we treat one row as an element, there's only one ordering of rows. That they actually have two from bottom to top, from top to bottom, but I think that's pretty much the same. So there's a very satisfying ordering of rows. But how do you do the LSTM on rows? Because these rows have some special structure. So it uses the one-dimensional convolution to replace the general matrix multiplication that is linear modules in traditional, in standard LSTM. So this is called the raw LSTM. The four functions is right here. This one is the convolution. So instead of doing the matrix multiplication, it uses the 1D convolution on this one to generate the say the hidden state and all the other things. So this one is called the raw LSTM. And if we want to do the pixel things, one of the order is something like this one. So this one is called a diagonal by LSTM. So because this one is prefused than this one, and then this one is prefused than this one, before this one. So if we kind of skewed the offsetting of this grid, then we can do this column verse, then do this column, then do this column, and then do this column. And doing it looks like a convolution, locally convolution things. But with states, of course, because LSTM is one by one. It's one by one, so you can do this thing one by one, parallel. Also, this one is called a diagonal by LSTM. Just like I said, PixelRNN has a very delicate very complicated design. So it actually has 12 layers and has several residual connections and maybe some. So it is very complicated and well designed. Considered by it was designed in 2016. So you can basically do the same thing with a CNN. Basically, you can do a convolution because convolution is very look-like. But in the first paper, we have listed 2 papers in the reference. In the first paper, the PixelCNN does not perform as good as the PixelRNN. So that's one problem. So because CNN is more efficient to train. For training, it is much faster than just using the LSTM. It doesn't make much sense that why CNN cannot generate something as good as LSTM in principle, at least in theory or in principle. However, they find out one important aspect that probably because LSTM and the GRU has some design that the traditional convolution networks does not have. So that might be the reason that LSTM and GRU perform better than the PixelCNN. Not because the inherent architecture of LSTM and CNN, because they are actually quite similar if we really consider about how it works. So the difference is in detail. Okay, so it find out that in LSTM it has some gate, like what we introduced in discussing last week. It has some forget gate and a bunch of different gate. The difference might be because they use some gate, but CNN does not have something. The gate is something times something, kind of like what the attention is. Attention is also something times something. We got a bunch of factors and a bunch of others, and we do the actually they do a dot product or do some product one by one and get a new result. We have a quadratic operation. So for here, this one is a get. So they put a get into convolution layers and code it as a gated convolutional layers. It turns out it improves the performance a lot. Also, that is, first, if we wish to use autoregressive setting, the convolution has a square kernel, so it will see the future. So the future means the pixels that has an order after the center pixel. So it contains future information. So you need to do something in order to omit, to mask out the information that should not give to this pixel. Otherwise, we cannot just. If we already know the future pixels, then there's no point to actually generate the image because we already know the pixels. So the whole autoregressive generating things is we only know the past information. We don't know the future information. So we need to do something. Also, that is called a mask. There are some subtle things you need to consider about, but basically it's quite straightforward. But the interesting thing is that it's introducing the gated convolution layers. So which one is very interesting, and it's a very useful technique that you can use to control your network. So in the implementation of my similarly complicated implementation of a network to do the language generation, I use something kind of similar to this one. Not exactly the same, but sort of similar in some sense. At least it has some multiplication of the output generated by 2 layers. And so this one is a very interesting construction block. Okay, so that's over it today. But although I didn't give a homework assignment for the PixelCNN, but once you have models that can do the auto integration, you will have one. Since because you are doing your homework, then you will have one. So you may want to try it on an image to see how it performs, and if you have a chance, compare it with the real PixelCNN and to see how what is the achievement of this result.